Bismillahirrahmanirrahim. I welcome all the engineering students, especially the students of Khwaja Farid University of Engineering and Technology in the course of the Heat and Mass Transfer. This is lecture number 12. Today we will discuss the same chapter actually, and we will discuss convection boundary layer. First of all, the terms which will be used when we move forward in this lecture, and these terms are slightly new for the students, and they are repeatedly used in this lecture. So therefore, I have enlisted all these terms. First of all, the specific molar flux, which is denoted by Na-S, which is in kilomole per second per meter square, and the species molar rate is NAS. Rate means total kilomole per second. Species mass flux is NAS, kilogram per second per meter cube. Species mass rate, which is NAS. It is not with the double dash in the superscript. It's kilogram per second. Species molar concentration is Ca, kilomole per meter cube. Species mass concentration is rho A, kilogram per meter cube, is basically a density. Specific molecular weight, which is the molecular mass of an element or a compound, is Ma, is kilogram per kilomole. Convective mass transfer coefficient Hm, it is meter per second. Just like convective heat transfer coefficient, here we have a convection mass transfer coefficient, which M denotes the mass transfer meter per second, and then and a very important term that is called binary diffusion coefficient, which is a new term, and DAB. AB means the two species A and B, because it is the mixing of the two streams, two species, like air flow over the water or air flow over some sublimate, right? So in this case, the mass is being transferred, evaporation process or sublimation process will take place. So it always between the two, it's a binary, means two, A and B. So there is a binary diffusion coefficient, is DAB, is meter square per second. What I have discussed regarding the DAB, that is the binary diffusion coefficient. What do you mean by the concentration boundary layer? Actually, this is one of the species which is flowing at a concentration is that concentration is kilomole per meter cube, right? That is the species which is flowing, and that is denoted by infinity. And we have a mixture of A and B. Its free stream velocity is U infinity. It flow, for example, over this plate, and of course it may be a water or it may be any sublimate, and is flowing, right? Similarly, what will happen, that a region is being developed where the concentration or the concentration boundary layer becomes equal to the 0.99 of the free stream concentration. Means I can say that this is the concentration Ca at any instant. If you see, this graph is in the backward direction. As long as you are moving in the forward direction, what will happen? The rate of evaporation or rate of sublimation or rate of the transfer of the species B with the species A, it is decreasing. So whenever air moves over the surface of a pool of water, the liquid water will evaporate, and water vapor will be transferred into the airstream. This is one of the example of the two species and making the concentration boundary layer. This is an example of the convection mass transfer. So in this case, the mass transfer means the mass, in this case, the mass of the water is being evaporated and coming into the airstream. More generally, consider a binary mixture of chemical species A and B that flows over a surface. In general case, we are talking about the two species A and B. A is flowing and B is stationary, over which the flow is taking place. It may be water flowing over certain surface. The molar concentration is kilomole per meter cube of species A at the surface is Ca, and in the free stream, I say Ca infinity. At the surface, of course, we say Ca. At the free stream is Ca infinity. If Ca differs from Ca infinity, transfer of species A by convection will occur. Of course, if the concentration at any instant is less than the infinite or free stream concentration, then the heat mass transfer will occur by convection. For example, species A could be a vapor that is transferred into a gas stream. Species B, which is the gas stream, due to evaporation at a liquid surface, as in the water example I have given you, or due to sublimation at a solid surface. It may be a sublimation, for example, it's passing over a camphor or ammonium chloride or iodine, right? Then water vapors or any gas is passing, so therefore it is the species sublimate from the surface and going into the gas. In this situation, a concentration boundary layer will develop that is similar to that of the velocity and thermal boundary layer. The concentration boundary layer is the region. This is a definition. The concentration boundary layer is the region of the fluid in which concentration gradient exists, and its thickness, that is delta C, is typically defined as a value of y for which at any direction of y where CAS minus CA divided by CAS minus CA infinity. This is the gradient of the concentration at any instant divided by total gradient, that if this is equal to when it becomes 0.99, this is the critical thickness of the concentration boundary layer. I again repeat, CAS minus CA is a gradient which exists at any point along any point, and then CAS is minus C infinity is the total gradient. This ratio becomes 0.99. Then at that point, the thickness in the y direction of the concentration boundary layer, that becomes delta C. This is the thickness of the concentration boundary layer. Above this, difference is not very significant. So to determine the rate at which this transfer occur, right? So we are interested in the molar flux of species A. What is the molar flux of species A? How the species A is being transferred, kilomole per meter square per second, is Na double dash. It is helpful to recognize that the molar flux associated with species transfer by diffusion is determined by an expression that is basically analogous to Fourier's law, and it is called Fick's law. It's just like minus Ka, where dt by dx, here Na double dash is minus dAb is curly Ca by curly y. So this is very much similar to Fourier law. This is called Fick's law. Okay. Na, the molar flux of species is being transferred, that is dAb curly Ca by curly y, where dAb is basically the boundary diffusion coefficient between, boundary means of course between the A and B. At any point corresponding to y is equal to 0 in the concentration boundary layer of species transfer is due to both bulk fluid motion, this is advection, and diffusion. Of course, at y is equal to 0, of course in the concentration boundary layer, the species transferred is both by means of the bulk motion, that is the motion of the fluid, and of course the advection, that is we say Na double dash As, that is equal to minus dAb curly Ca by curly y at y is equal to 0 at the surface, where we say y is equal to 0. So that is both the transfer due to the bulk motion and due to the advection, and this is the advection at y is equal to 0. So analogous to Newton's law of cooling, an equation can be written that relates the molar flux to the concentration difference across the boundary layer. In the same way that we had discussed in the Newton's law of cooling, we can also write this equation for the mass transfer to do convection. So Na double dash S is equal to Hm Cas minus Ca infinity. It's just like Ts minus T infinity in the case of Newton's law of cooling. Now, where H is of course the convection mass transfer coefficient in meters per second, and that is analogous to the convection heat transfer coefficient. So, so the heat transfer taken place due to this, that is basically due to advection, and due to the analogous Newton's law of cooling, if we compare this equation with this equation, these are equal heat transfer. So we get HM, that is convective mass transfer coefficient. It minus DAB, curly CAB, curly Y, at Y is equal to 0, CAS minus CA infinity. We are taking remember that this should be taken at Y is equal to 0 at the surface. That is the maximum convective heat transfer, convective mass transfer coefficient. What is the significance of this concentration bond layer? For a flow over any surface, there will always exist a velocity bond layer, and hence there is a friction, surface friction. Likewise, a thermal bond layer and hence convection heat transfer will always exist if the surface and the free stream temperature differ. Right. So when the flow in the hydrodynamic, there is a velocity gradient due to friction, and that causes the shear stresses. And similarly, like the thermal bond layer, there is a difference of temperature, right? And this will create the thermal bond layer. Similarly, a concentration bond layer and convection mass transfer will exist if the fluid species concentration at the surface differ from a species concentration in the free stream. When the concentration of the species at the surface differ with the concentration in the free stream, then there is a bond layer exists which is called concentration bond layer. So remember that the variation in the velocity over the surface in the y direction cause the hydrodynamic bond layer, velocity bond layer. The difference in the temperature will cause the thermal bond layer, and the difference in the concentration from the surface and into the free upstream concentration, that causes the concentration bond layer. The velocity bond layer is of extent sigma x, and it is characterized by the presence of velocity gradient and shear stresses. Of course, they are basically denoted by delta x, and this is basically change in velocity which causes the shear stresses. The thermal bond layer, we say delta t, and is characterized by temperature gradient and heat transfer. The concentration bond layer is of extent, we say delta c, c for concentration, and is characterized by concentration gradients, the change in the concentration and species transfer, right? So here in the case of a velocity bond layer, the velocity gradient; in case of temperature, the temperature gradient and heat transfer. Here, of course, we have concentration gradient and species transfer, mass transfer. Situation can arise in which all three boundary layers are present. There are certain number of cases in which we have all the three, that velocity boundary layer, thermal boundary layer, and concentration boundary layer. So let's focus on the mass transfer. Similar results may be obtained for convection mass transfer, that as we have obtained for the convection heat transfer. If a fluid of species smallest concentration, Ca infinity, there is a concentration, free stream concentration, flow over a surface at which the species concentration is maintained at some uniform value, where the species concentration at the surface, of course, is not equal to species concentration in the free stream. Transfer of species by convection will occur. So when there is a difference of concentration at the surface and in the free stream, of course, the species will transfer by convection. The total molar transfer rate for an entire surface, that is Na kilomole per second, may be written as Na is equal to HMAS CAS minus CA infinity. It's just like this. We have already written Na double dash. Double dash is for the per unit area. When we say Na, that is the number of kilomoles per second total. So that is H bar M AS CAS minus C infinity, just like H bar AS TS minus T infinity in the case of Newton's law of cooling. So it's the same analogy we have derived. So the average and total mass transfer coefficient are related by an equation of the form. This form is your students to see. It's very much similar that we have written for the average overall heat transfer coefficient, overall convective heat transfer coefficient. Similarly here also H bar M, the overall or average average mass transfer convection coefficient is equal to 1 by AS, the surface area, integral over the surface area HMDAS. It's just like H bar is equal to 1 by AS, integral over the surface area HDAS in the case of convection heat transfer coefficient, overall heat convection heat transfer coefficient. Similarly here, it is H bar M is it is the overall or average convection mass transfer coefficient is equal to 1 by AS integral over the surface area HMDAS. So it's the same analogy, and similar formulae are there. So this is the we say this is the velocity of the free stream, and this Ca is the free stream concentration of species A, right? So for this plate, we can if we are taking off the plate, then of course we take the length L, the variation of the y is ignored. So H bar M is equal to 1 by L 0 to L HM dx. That as we have written for the convection heat transfer coefficient, H bar is equal to 1 by L 0 to L H dx, right? So species transfer may also be expressed as a mass flux, that is kilogram per meter square second, or as a mass transfer NA kilogram per second, by multiplying both sides of the equation. That these equations are being multiplied by both by the molar masses. If you multiply with the molar masses, that will be converted into kilogram per second. Let's see, I'm showing here that a mass transfer NA double dash is equal to HM rho AS minus rho A infinity. That is the molar transfer. That is the molar transfer at kilogram per meter square per second, right? So this is the density of the species at the surface, the density of the species at a free stream. Similarly, if I multiply with the area, I get the total, that is NA H bar M AS rho AS minus rho A infinity, and that is basically in kilogram per second mass flow rate. So where rho is of course the density I show you. Fixed law. Fixed laws of course can be written as, you know that in terms of this, in terms of mass transfer, that is NA double dash S, which is kilogram per meter square per second, is equal to minus DAB rho curly rho A by curly Y, right? In the previous case, the concentration would say curly CA by curly Y. Here we write minus DAB curly rho A by curly Y at Y is equal to 0, and of course this is the mass transfer kilogram per meter square per second at Y is equal to 0. So multiplying this equation 6.9 basically with molecular mass, another relation for HM can be obtained. The convective mass transfer coefficient HM minus DAB, this becomes rho curly rho A by curly Y at Y is equal to 0, right? I compare these two equations, this one and this one, we get rho AS minus rho A infinity. Again, I explained this equation and this equation to be compared, right? This is an A star. So we compare these two, we get minus DAB curly rho A by curly Y is equal to 0, rho AS minus rho A infinity. This is the convective mass transfer coefficient, with the units are meters per second. To perform a convection mass transfer calculation, it is necessary to determine the values of the CAS or rho S. Either you go in the concentration terms, that is kilomole per meter square per second, or you would go for the kilogram per meter square per second, or either in the mass term, either in the mole terms. First of all, we know these things. Such a determination may be made by assuming thermodynamic equilibrium at the interface between the gas and the liquid or the solid. We say that either the liquid transfer between the gas and the liquid, or between the liquid or solid or gas and the liquid, they are in equilibrium. In equilibrium. So one implication of equilibrium is that the temperature of the vapor at the interface is equal to surface temperature, right? So vapor temperatures are equal to surface temperature. A second implication is that the vapor is in a saturated state, right? No more things can be added, no more vapors will be added in that particular species, in which case thermodynamic stable This is in the same way that we have written for the general gas equation, P is equal to nRT, P is equal to mRT. So here we also have CAS is equal to P saturated TS over RT, RTS. This is P saturated. We take the P saturated, P saturated at a saturated temperature over RT, and that is the concentration of the species A over the surface. Now, species boundary layer equation and similarity that we dear students, what similarity calculation we have done for the velocity and the thermal boundary layer, we will also do this for the concentration boundary layer. Species boundary layer approximation, like in the case of velocity, here we also assume that the Cully square Ca by Cully x square is very much less than Cully square Ca by Cully y square. In the case of velocity, we assume that Cully square u by Cully x square is very much less than Cully square u by Cully y square, and similarly Cully square t over Cully x square is very much less than is Cully square t by Cully y square in the case of thermal boundary layer. So this is the same assumption here. Of course, the variation in the concentrations in the x is very much small as compared to the concentration along y direction. So species equation for a non-reacting boundary layer is u Cully Ca by Cully x plus v Cully Ca by Cully y is equal to dAb Cully square Ca by Cully y square. These equations we have written already in the basics in the first lecture of this chapter. So this equation is obtained by applying the conservation of a chemical species to the dx dot dy. We take a small volume, right? You know that, take a small volume element dx dy, and there is a length of one differential control volume. Term on the left hand side account for the net transport of species A, right, due to the bulk fluid motion, that is called advection, while the right hand side represent the net inflow due to the y direction diffusion, right? So this is basically the advection term, and this is basically the diffusion term. So this left hand shows the transfer or transport of species A due to bulk motion, and the right hand side represent the net inflow due to the direction, due to y direction diffusion, towards the diffusion in the y direction. And you see the concentration boundary layer graph, it is initially wider at the surface, and you move into the free stream, it is decreasing. Of course, rate of the diffusion or rate of diffusion of species B in A is reduces, right? And if you see, you see this one, sorry, this is temperature, this is concentration. Velocity is increasing. Similar, it's the same, almost the same trend in the case of a thermal boundary layer. So we derive this equation for the similarities using the similarity variables, dimensionless form of species boundary layer equation. The same assumption that we have made, u star, dimensionless parameter, u or v. U is a velocity, right, in the x direction at any instant or total velocity. V star is equal to v over v. X star is equal to x by L. Y star is equal to y by L. We know Cully square u Cully Ca by Cully x plus v Cully Ca by Cully y is equal to dAb Cully square Ca by Cy. Ca star that we defined is Ca, the concentration at any instant, minus Ca, the concentration at surface, over Ca infinity minus Ca, the maximum gradient or available gradient. If we divide this becomes again a dimensionless parameter. So we put this value here. You see, this becomes what is u? Of course, u is equal to u star times v, and this is x becomes L Cully star Ca by Cully x. This x is becoming from x is equal to x star L. So L is constant. We take off this out of this derivative. The same thing happened here. So dAb, and I did the same thing, Cully square Ca by Cully y square. So y square is y becomes y star L. So this becomes L square, right, out of this, and y star is the variable. So by taking some common and doing this, we take of course this is if you see L is common, L will be cancelled out. I get u star Cully Ca star by Cully x star plus v star Cully Ca by Cully star Cully y square dAb, and we divide with VL, of course common, and I multiply with rho by mu or rho by mu, and Cully square Ca by Ca, Cully square Ca by Cully star y square. So this is dAb rho VL upon mu. If you see, this becomes rho this becomes rho VL by mu. This is rho VL by mu, and this becomes the Reynolds number, and the this is the 1 over nu, right? This is 1 of kinematic viscosity, and curly square Ca star by curly Y star. So we get the DAB Reynolds number dot 1 over nu curly square Ca star by curly Y star. So here we define another dimensionless number that is called Schmidt number. That's SC, that is basically nu over DAB. This nu over DAB is called Schmidt number. So I write it here, DAB or Reynolds number into Schmidt number, curly square Ca by curly star Y square. And of course, the students, you know, the nu is the kinematic viscosity. So nu is the kinematic viscosity, and DAB is basically the Barney diffusion coefficient. So this ratio is a Schmidt number. So basically Schmidt number is a dimensional number, is a ratio between the viscous diffusion. This is a diffusion due to viscous, of course, kinematic due to viscosity, over molecular diffusion, right? This DAB is basically the Barney diffusion. That is the due to the there's a diffusion because of the motion of the molecules, right? And this is the diffusion because of the viscosity. So it's the ratio of the viscosity diffusion rate over molecular or mass diffusion rate. So Schmidt number is again a dimensionless number, is the kinematic viscosity over DAB, that is the Barney diffusion coefficient. It is the ratio of the viscous diffusion. These two parameters clearly show this is the diffusion due to the viscous effects, and this is due to the molecular mass diffusion concept, due to the diffusion. Functional dependence, of course, Ca, I said the same thing that we have done for the thermal boundary layer and velocity boundary layer. Ca, the concentration depends upon is a function of x, y, Reynolds number and the Schmidt number. Hm, we have also already written the mass transfer coefficient in meters per second minus the AB, curly Ca by curly y is equal to 0, Cas minus Ca infinity. So Hm is equal to minus dA by dl, Ca infinity minus Cas over Cas minus Ca infinity, curly Ca star over curly y star at y star is equal to 0. I just put the value of Cas minus C infinity for my dimensionless parameter which I defined here, right? So this one I have put it here. So Ca star, right? This is Cas minus Ca infinity. So Cas minus C infinity. I put this value of this value Cas minus Ca infinity becomes this. So I put this value here. So Ca infinity minus Cas over Cas minus Ca infinity. So it's curly Ca star by curly y square, y star equals 0. If you take minus common, this is cancel out. It's dAb by L, curly star Ca by curly star Ca by curly y star at y star is equal to 0. This is the convective mass transfer coefficient in the of course the dimensionless parameters. Local convection mass transfer coefficient, of course the local one is Hm by L is Hm by L dAb is equal to, right, Hm, and I have taken this one on the left hand side, is become HML by dAb, a curly Ca star by curly y square is 0. So this is equal to the Shroud number, which is a function of x star, Reynolds number and the Schmidt number. And SH is called, of course, local Shroud number, and Shroud number we have defined HML by dAb, convective mass transfer coefficient, length, and the Barney diffusion coefficient. This again show you is the mass transfer. This is transfer because of the convection, and this is the mass transfer because of diffusion. So it is the ratio of the mass transfer by convection to the mass transfer by diffusion. So heat and mass transfer analogies. So these analogies we have wrote Nusselt number over Prandtl number n is a function of x star and the Reynolds number, and the Shroud number and the Schmidt number raised to power, and they are similar. This is the similar term come from the heat transfer, of course, convective heat transfer, and this term is basically for the of course the mass transfer, right? So this is HL by K in Prandtl number, Nusselt number is, this is HML by dAb over the Schmidt number. So if I need to find the ratio of the convective heat transfer coefficient and the mass transfer coefficient, so from this equation, this is little blurred. So H over HM is equal to 1 over DAB, right? Because this L and L cancel out. So H over HM will be equal to 1 over DAB, Prandtl number raised to power n and Schmidt number raised to power n, which is equal to, of course this is also K, this K by DAB, K by DAB. Basically we are comparing these two Nusselt number HL by K, and this is HML by. So 1 over DAB is Prandtl number raised to power n, Schmidt number raised to power n, which is equal to K by DAB is the Lewis number minus n. So we define a new number here. K is of course the thermal conductivity, DAB is the binary diffusion coefficient, and LE is the Lewis number. So Lewis number is alpha over DAB, or is the ratio of the you can say Schmidt number to the Prandtl number, that is alpha over DAB. And this is K alpha, you know that alpha is equal to K over rho Cp, the diffusion coefficient, and that is DAB. So Lewis number is the ratio of the Schmidt number to the Prandtl number raised to power n. So Lewis number is K over rho Cp DAB in terms of the parameters, that is depends upon the thermal conductivity, density, specific heat, and the binary diffusion coefficient. Again, it is of course the ratio between the two terms, that the Lewis number is basically the ratio of the thermal diffusivity to the mass diffusivity, right? It's the thermal diffusivity to the mass diffusivity, because this is K and this is because of the mass, right? Because this is K is because of the thermal, and this is because of rho CPDA is the mass diffusivity. The thermal diffusivity of the mass diffusivity. So if I take this term, so which one? I'm taking this one. So this K over DAB, I multiply and divide with rho Cp over rho Cp into L Lewis number minus n in the previous equation. Continue, right? So this becomes K over rho Cp DAB rho Cp Lewis number n. This becomes this, and I multiplied the denominator with this, right? So why I did this? Rho Cp into Lewis number. So this is equal to rho Cp Lewis number 1 minus n, because sorry, we write K over rho Cp DAB is the Lewis number. So this becomes in the this becomes also the minus of this, of course, K over. So this is 1, this is Lewis number, this is also Lewis number minus n. It becomes a smaller value, more compact terms, rho Cp Lewis number. It means H over Hm, the convective heat transfer coefficient to the mass transfer coefficient ratio, is just depends upon the density, the specific heat, and the Lewis number, which is thermal diffusivity of the mass diffusivity ratio. Thank you very much, dear students. In the next lecture, I will discuss some mass transfer parameters and solve the problems regarding the mass transfers. I hope you understand number of things which is not clear regarding the concentration boundary layer. Next lecture will be regarding the application of this concentration boundary layer and problem solving examples and the problem. Thank you.